Welcome to the first part of the course, Infrared Spectroscopy. It is obvious from the name itself that this spectroscopy deals with the infrared region of the electromagnetic spectrum. So, we'll begin with a brief introduction and then we'll look into harmonic and anharmonic oscillators. And why we look into these oscillators is to understand the vibrational motions of the molecule as an oscillator. And then we'll discuss degrees of freedom with examples. Infrared spectroscopy is also called the vibrational spectroscopy, and that is because the vibrational energies of a molecule lie in the range of infrared region in the electromagnetic spectrum. And it is important to note that, like we are in quantum chemistry and we are familiar with other types of energy, likewise, vibrational energy of a molecule is also quantized, and that can be calculated from the Schrodinger equation. And now this is important. A molecule is said to be infrared active only if there is a change in its dipole moment. And I think it's worth repeating that a molecule is infrared active only if there is a change in its dipole moment. And in our discussions, we assume that the rotational and vibrational motions are independent. That is, they do not interfere with each other. We are all familiar with simple harmonic motion. Well, in this case, we consider a molecule as a simple harmonic oscillator. And considering only the vibrational state, the Hamiltonian or the energy operator is given by this equation. And now here we have the potential energy term and the kinetic energy term. And the vibrational states comes out to be something like this, where psi of x in a vibrational state V is given by nv times a Hermite function times an exponential function. Here nv is the normalization constant, we have an exponential function and a Hermite function. We have the value of the Hermite function for the vibrational quantum number V equals 0 as 1 and the value of the Hermite function for vibrational quantum number 1 as 2x, and the following vibrational function values can be found using this equation. Considering the vibrational motions of a diatomic molecule, we have the wave number given by this equation, nu bar equals 1 by 2 pi c, where c is the speed of the light, times under root k by nu, where k is the force constant and nu is the reduced mass. In case of a diatomic molecule, we have nu equals m1 m2 by m1 plus m2, where m1 and m2 are the masses of the atoms of the molecule. And we have the energy term given by this equation, EV, where V is the vibrational quantum number, equals V plus half times h times nu, where nu is the frequency of the vibration. This is the energy versus internuclear distance curve of a simple harmonic oscillator. So we have different states corresponding to different vibrational quantum numbers like 0, 1, 2, etc. This state corresponds to the vibrational quantum number 0, and the energy corresponding to this state is what we call the 0 point energy. And we have other states corresponding to other quantum numbers. Quantum number 1 corresponds to this state, vibrational quantum number 2 corresponds to this state, and so on. Well, a transition from a state to any other state is not possible in case of a harmonic oscillator. There is a selection rule which states that the change in vibrational quantum number must be plus or minus 1 for a transition to take place. So a transition from quantum number 0 state to a quantum number 1 state is possible, but a transition from a 0 quantum number state to quantum number 2 state is not possible. We know that the real molecules do not obey the laws of simple harmonic motion. We know that they actually dissociate as the atoms go far away from each other. So a more clear picture of a molecule vibration is given by the anharmonic oscillator or the Morse oscillator. In this curve, the green curve corresponds to the harmonic oscillator and the blue curve corresponds to the anharmonic oscillator or the Morse oscillator. We find that at lesser internuclear separation, the anharmonic and harmonic oscillators overlap. But as you increase the internuclear distance, they differ in values. We have the potential of an anharmonic oscillator given by this equation, and the energy of a state corresponding to a vibrational quantum number V is given by this equation. EV equals V plus half times nu E bar, where nu E bar is the wave number corresponding to the equilibrium oscillation. minus v plus half whole squared times nu e bar into xc, where xc is called the anharmonicity constant, which comes due to the anharmonic behavior of a molecule. When transitions take place in a harmonic oscillator, we saw that it is possible only if delta V equals plus or minus 1. And we observe from this curve that as the energy increases, the energy difference between two states decreases. So as delta E tends to 0 at dissociation limit, we have a maximum possible vibrational quantum number, and this value equals Vmax equals 1 by 2 Xe minus 1. When do we say that a molecule is IR active or infrared active? Well, there are two conditions. One, that the frequency of the radiation equals the vibrational frequency of the molecule. Two, there should be a change in the dipole moment of the molecule. Speaking about the degrees of freedom that a molecule can have, a linear molecule can have 3n minus 5 degrees of freedom, and a non-linear molecule can have 3n minus 6 degrees of freedom, where n is the number of atoms in the molecule. These are few examples of the normal modes of vibrations in a molecule. And a normal mode of vibration is defined as a molecular motion in which all the atoms move in phase and with the same frequency. Now let's look at the degrees of freedom of carbon dioxide. The blue shaded circles indicate the carbon atom at the center, and the white ones are the oxygen atom. So in the first one, both the oxygen atoms are moving in the opposite direction. In the second mode, both the oxygen atoms are moving in the same direction. And in the third mode, when the oxygen atom is coming out of the screen, the carbon atom goes into the screen. And in the fourth mode, the atoms move in the specified direction as shown. But which of these modes are IR active? Well, we have discussed that a molecule is IR active only if there is a change in dipole moment. Well, in the first case, as the molecule vibrates, the change in dipole moment is zero. So it is IR inactive. While all the other modes have a change in dipole moment as they vibrate, and so all the others are IR active. And we observe that the third and the fourth mode of vibrations have degenerate or identical energies. So there will be only one peak for both these modes. We have discussed in one of the previous slides that the wave number of an oscillation is given by this equation. Nu bar equals 1 by 2 pi c times under root k by nu. And from this we infer that the wave number is directly proportional to the root of k and inversely proportional to the root of the reduced mass. As triple bond is stronger than double bond than a single bond, the force constant is highest for triple bond. So a peak in the spectrum happens at higher energy or higher wave number. So a peak in the spectrum happens at higher energy or higher wave number value than a CC double bond. And similarly here, the atom attached to the carbon increases its mass from left to right. So higher reduced mass means lower is the energy at which a transition in the vibrational states can occur, and hence the wave number or energy of transition decreases from left to right.